For today's lesson, we are going to be doing things slightly differently than we have done up to this point in the course. Half of today's video will be devoted to the history of set theory, the ideas that led to its foundation, why it was a necessary development in the history of mathematics for set theory to come about when it did. While Cantor gets the credit for it, as we will see, the ideas that Cantor set forth were already implicitly being used by his contemporaries. In front of us we have Richard Dedekind, which we'll get to in just a moment, who also had the ideas of set theories being developed around the same time as Cantor. A consequence of today's discussion that I want to emphasize is this aspect that we tend not to see in our mathematics courses or in our mathematics texts. Mathematics spans decades, if not centuries, for it to be developed precisely. As you've worked through the exercises that we have done for homework as well as the exam for this course, some of these results were at one point what would have gotten you a PhD back in the 1800s. Yet, today, because we have this machinery, we know the shortest paths to prove certain results, it seems that we can get this almost instantaneously, when in reality, as we will see, the time from one result to the next took years. Yet today, we can do it in the span of days, if not weeks, in our problem sets. And this is something to be mindful of as you progress in your mathematical courses. Every course that you take will have you investigate an area of mathematics that took decades, if not centuries, to develop completely. And so, let us begin. 1872, Richard Dedekind defined what it meant for a set to be infinite. Now, is this to say that mathematicians prior to Dedekind did not have a notion of what it meant to be an infinite set? No, mathematicians had a notion of what it meant for a set to be infinite. The real numbers are infinite, the integers are infinite, but no one had precisely stated a definition of what it meant to be infinite. And that's the crucial distinction when it comes to Dedekind. He, as well as Cantor, who, as we will see, in the same year gave a definition for what a set to be infinite was, yet they did not call it a set yet. Implicitly, we know it today to be a set. So what was Dedekind's definition for what it meant for a set to be infinite? So his definition was as follows. A set S is infinite when it is equinumerous to a proper subset of itself. In the contrary case, S is said to be finite. We can interpret this definition in the language that we have covered so far as follows. A set S is said to be infinite if there is a proper subset B of S such that B is equinumerous to S. In the case of a finite set, we have proven in our last lesson, if you have a proper subset of a finite set, the cardinalities of the two sets cannot be equal. Therefore, we have that the sets are finite by Dedekind's definition. That same year, Cantor also gave a definition of what it meant for a set to be infinite. Now, both Cantor and Dedekind approached this formulation of what it meant for a set to be infinite by their motivation to rigorously define the set of the real numbers, which up to that point was taken as an intuitive definition. And that was a big problem in the 1800s, well actually anything before the 1800s, that was one of the big problems in mathematics. Proofs were based on intuition. The method of formal proof that we have today came about from our coverage of set theory. In the 1700s, 1800s, 1600s, anytime before, it was easy to get by saying, well, this seems to be obviously to be true, so it is true. And that was a sufficient explanation for a proof if other mathematicians also believed that your argument was indeed intuitive. Set theory gave us the tools to remove the need to rely on intuition, but prove things based on the axioms of set theory. Now, to showcase this aspect of what I mean by results being proven on intuition, let me consider one example from calculus that you have seen. In 1734, Euler proved the following. If U is a set of R2, and specifically U is an open disk in the plane, and F is a function whose domain is the set U, and whose outputs are real numbers, and that function is differentiable everywhere on U, then the partial derivative of f with respect to x and then y of a comma b is equal to the partial derivative of f with respect to y then x of a comma b for every single a comma b in U. When you do calculus, you have seen this theorem, but the story is actually more interesting because this theorem is not correct. Yet, various proofs of it were found in the century following Euler's theorem. So, for example, Clairaut gave another proof of Euler's theorem in 1740. Lagrange also discovered a new proof in 1797, and Cauchy in 1823. Now, each of these proofs were wrong, but it was not until 1867 when Ernst Lindelof proved via a counterexample that each of the theorems that Euler, Clairaut, Lagrange, and Euler had proven were wrong. And he gave the following counterexample. If you take the function f of x comma y, which is equal to x times y, x squared minus y squared, over x squared plus y squared, if x comma y is not equal to the origin, and 0 when it is equal to when the input is the origin, then you can prove that f of x comma y of the origin is not equal to f of yx at the origin. And so the theorem is false. And if you go back to your textbooks, your calculus textbook, what you'll see is that the theorem that is in your textbook is not this one, because of course this is wrong, but rather what is known as Clairaut's theorem, which was actually proven by Hermann Schwarz in 1873. And so here is the formal statement of Clairaut's theorem, and the way to fix the theorem statement that Euler and others have proven was to add a condition on f. It is not enough to simply have that the function is differentiable on its domain. One also requires that both the partial derivatives fxy and fyx are both continuous on the domain U. But now, the thing I want you to keep in mind with this is that it was not until 1873 that the correct theorem was published. Yet, in the 100+ years between Euler's original proof in 1734 and the counterexample found in 1867, other mathematicians used this theorem to prove results. And each of those theorems is now at risk of being incorrect because they are based on a faulty statement. And this is a problem in mathematics because we are always building up. We're building on the work of our predecessors. But if their published theorems are wrong, then everything that follows could also be wrong. And as we have seen from our coverage of truth tables at the beginning, from a false assumption we can prove anything. And that is something that in the 17 and 1800s, especially in the 1800s, as we get closer to the 1870s, that was at the forefront of the minds of mathematicians. How can we be sure that the literature is actually correct when there are numerous documented theorems that are actually not correct? As another example, let me go ahead and tell you the story of Monsieur Leblanc. So we're going to go back to 1808, right after the French Revolution. So now this is in the era of Napoleon. Pierre Simon Laplace was a mathematician, but he was also the Minister of the Interior to Napoleon. And in 1808, he introduced German physicist Ernst Shanley to Napoleon. And Shanley showed a certain experiment to Napoleon which got Napoleon's attention. So let's see a visualization of the experiment that Shanley demonstrated to Napoleon. The experiment that Shanley demonstrated to Napoleon was the following. Take a plate and sprinkle sand or salt on top of that plate. What happens when the plate vibrates with a given frequency? And so here is the demonstration. So now here's a frequency being applied to cause the plate to vibrate. And notice how the particles form geometric patterns. So this raises the following question. Is it possible to find a formula that tells us if we apply a certain frequency, these are the patterns that will arise? And that was the question that Napoleon asked. To quote the Paris Academy of Science in April 1809, His Majesty the Emperor and King, being struck by the impact that the discovery of a rigorous theory explaining all phenomena rendered sensible by these experiments, meaning the experiments due to Shanley, would have on the progress of physics and analysis, desires that the class make this the subject of a prize. The class has thus proposed for the subject of the prize the development of a mathematical theory of the vibration of elastic surfaces and a comparison of this theory with experiments. And as such, the Paris Academy of Science introduced the Prix Extraordinaire, the extraordinary prize for whoever solved this experiment of Shanley. The prize for the Prix Extraordinaire came with 3,000 francs, and 2 years later, an entry by Monsieur Leblanc caught the eye of the committee in charge of awarding the prize. Now, the proposed solution was incorrect. The results were ingenious. Lagrange was able to fix a certain portion of the argument, but it was still not enough to get a general theory. Fast forward several years later, so now we're in 1815, Monsieur Leblanc submitted a new proposed solution. And that solution was found to be correct, and Monsieur Leblanc was awarded the prize. But Monsieur Leblanc was not your typical mathematician of the time. Monsieur Leblanc was in fact Sophie Germain, a self-taught mathematician who had been publishing under the pseudonym Monsieur Leblanc so that she would be taken seriously by the mathematicians of the time. She solved the question that Napoleon posed to Shanley, which earned her the distinction of being the first woman to win a prize from the French Academy of Science. But she was not allowed to receive the prize in person because the French Academy of Science had a rule that the only women allowed in the establishment were the wives of their members. But she did present the solution correctly, and here it is. And so it is a partial differential equations. And so if you're interested in seeing results like these that describe natural phenomena, similar to what we just saw in the video, where that is not necessarily a natural phenomena, but it can be described via differential equations. And her differential equation is as follows. There's this equation right here, where the variables x, y, and t that you see here correspond to a function, f of x, y, t. And k here is a constant. Now the function is in terms of three inputs, x, y, and t. X and y can be interpreted as the points on the surface itself, and then t is time. And the output of the function is the amplitude at a given point and time. Now, how does this tie in with the discussion of set theory? While Sophie Germain's solution was correct, it was simultaneously not correct, but not due to fault of her own. She based her work on a result of Euler's that happened over half a century prior. and that result was wrong. And so here is the issue that is happening 1800s in mathematics. You have people who are proving theorems based on previous results that are now well known to be true, or so we thought, because the proofs were based on intuition. And now you have rigorous arguments based on those results that end up not being true. Thankfully, it was eventually, the error of Euler's was then found, and it did not take that much tweaking to actually get the correct solution based on Sophie Germain's techniques. Unfortunately, Sophie Germain is not remembered as much today for her work on elasticity, even though she was one of the founding members of the theory through her work. Because Poisson, a mathematician in the committee that refereed the submissions, quoted her work without giving her credit, and Poisson would later on develop the general theory. And so oftentimes in the history, Sophie's contributions are not discussed because Poisson usually takes credit even though he based his work on hers. However, she is best remembered for her profound contributions in number theory, specifically with regards to Fermat's last theorem. And so now I'm going to take a sidestep. We have not discussed Fermat's last theorem in this course, and so I want to go ahead and just give you a brief history and taste of this very rich question that in many ways led to the foundations of modern mathematics. At its core, Fermat's last theorem states the following. There are no solutions in the positive integers to the equation x to the n plus y to the n equals z to the n for n greater than or equal to 3. And so here n is a positive integer greater than or equal to 3. So in other words, things that we see as we study for, say, SATs, Pythagorean triples, so 3 squared plus 4 squared equals 5 squared. Solutions such as these do not exist the moment you change your squares to cubes. You cannot find solutions such as these in the positive integers. The story of Fermat's last theorem has been heavily romanticized. So this is something that is covered in detail in a number theory course, and so that's Math 312 if you're interested. And the story of Fermat's last theorem starts off in 1637 when Pierre de Fermat, a lawyer, not a mathematician, wrote the following in his copy of Diophantus Arithmetica. He wrote this marginal note that it is impossible to separate a cube into 2 cubes, or a fourth power into 2 fourth powers, or in general any power higher than the second into 2 like powers. And then he says, I have discovered a truly marvelous proof of this, which this margin is too narrow to contain. It is incorrectly stated by many that Fermat had a proof, and that is not true. He wrote this note in the margins of a text, never expecting anyone to read that note. 4 years later, we know through his correspondences that he did prove Fermat's last theorem in the n equals to 4 case, but he never claimed in any of his correspondences to have proven the general statement that we see in the marginal note. Now, after Fermat died in the 1660s, his son would publish the notes that his father had written in his copy of Diophantus Arithmetica, and that is where mathematicians first learned of this famous note that Fermat claimed. A total of 48 marginal notes, by the way, that Fermat had written in this copy. Now, the reason for the name last theorem is that of the 48 notes that Fermat had scribbled throughout his copy of Diophantus Arithmetica, this statement, that it is impossible to separate a cube into 2 cubes, so on and so forth, that was the last statement to be resolved. And so it came to be known as Fermat's last theorem. And so here's a brief timeline of Fermat's last theorem. So 1637, Fermat wrote the famous marginal note. 1641, we know through correspondences that he had the n equals to 4 case. After Fermat died, Bessy found a proof of n equals to 4 case and proved it, because technically Fermat got this as a corollary, didn't publish, so the distinction of the first proof for the n equals to 4 case, so that is when we have x to the 4 plus y to the 4 is equal to z to the 4th, that has no positive solutions, no solutions in the positive integers. So that was done by Bessy. The next breakthrough came in 1738 when Euler simplified Bessy and Fermat's proof and for the n equals to 4 case, and Euler devoted his lifetime to solving the various claims that Fermat stated in his marginal notes. And in 1770, he finally succeeded in proving the n equals to 3 case, which he technically had done in 1753, but that proof was incorrect. And so it took him almost 20 years to fix his error. And so what I want to draw your attention to now is that as we get to 1825, it has now been almost 2 centuries since Fermat originally scribbled that note in his copy of the Alphantis Arithmetica. And then something profound happened in 1823. Sophie Germain was able to break down Fermat's theorem into 2 statements, and she was able to prove one of them. By breaking it up into 2 cases, she gave a program for being able to prove Fermat's theorem in generality, something that mathematicians up to that point had not done. The general consensus was to do it for one exponent at a time. Fermat did 4, Euler did 3, so next you do 5, and then you just continue doing one exponent at a time. That was the general consensus in the 1800s, since there was no one knew how to do it in generality. With Sophie Germain, what occurred was that following the awarding of the prize from the French Academy of Science, the French Academy of Science stated that they would then award a new prix extraordinaire to whoever solved Fermat's theorem. And Sophie Germain, having won the prize, now decided, I am going to learn everything I can about the history of Fermat's theorem, what has been done before, and try to prove it myself. And in doing so, she developed the program that I just mentioned, which would lead to a series of breakthroughs in the years that followed. Building on her work, Dirichlet and Lagrange did the n equals to 5 case, the n equals 14, n equals to 7, and then finally in 1847, Kummer culminated the work that Sophie Germain began with her program to prove it in a much more general setting for what are known as regular primes. And so that's just sort of a tidbit on Fermat's theorem. I am going to send an email with a documentary that if you're interested in learning about the modern proof of Fermat's theorem, specifically that of Andrew Wiles and Richard Taylor in 1994, then I highly recommend watching the documentary. And so it goes into more detail of what is happening between these statements right here, following 1955 to 1994. So now, let us return to the topic at hand, set theory. So we already discussed that Dedekind in 1872 published a definition for what it meant for a set to be infinite. That same year, Cantor introduced the notion of sets, as we have covered them in this course. In that article, he introduced operations on sets, union, intersection, set difference. But the plan of the paper was to rigorously prove what the real numbers were as a set. And so Cantor and Dedekind both have the distinction of being the first in giving a definition for what the real numbers are. Both of them gave 2 different definitions. Dedekind gave his proof on the real numbers, which is done via what are known today as Dedekind cuts. Cantor gave his via what are known as Cauchy sequences. If you take real analysis, you'll see Cantor's definition of how the real numbers are defined. Cantor's construction of the real numbers led him to start investigating the properties of infinite sets. Given that Dedekind had also published an article on the real numbers, Cantor reached out to Dedekind and asked him in 1873, are the real numbers equinumerous to the natural numbers? But Cantor answered his own question the following year, when he proved that the set of real numbers is uncountable. In other words, the real numbers are not equinumerous to the natural numbers. And this led him to start to investigate the properties of infinite sets further. In 1877, Cantor proved that for each positive integer n, the real numbers are equinumerous to r to the n. And he was so shocked by this result that he wrote to Dedekind saying, "I see it, but I don't believe it." And he asked Dedekind to check his proof. Now, this quote, the way that I'm phrasing it, it makes it seem that Cantor did not believe what he had just proven. He believed what he had proven. What he was unsure about was whether his proof was correct. And that was what his intent was in his letter to Dedekind. He had proven this, but he was unsure if his proof was true. So he did not believe that the methods by which he proved this result were accurate. And so he asked Dedekind to look over his work and verify that his proof was in fact correct. A year later, Cantor conjectured the famous continuum hypothesis. What the continuum hypothesis states is that if A is a subset of the real numbers, then A is equinumerous to the natural numbers, or A is equinumerous to the real numbers. So we'll discuss this conjecture further, but let's move on. Between 1878 and 1885, Cantor published a series of papers which cemented set theory as its own discipline. The topics that we have covered in our course on set theory up to this point are all contained, for the most part, in these publications from 1878 to 1885. The definition of equinumerous, the definition of a function, what it means to be bijective. All these ideas that we have been able to go through in the span of weeks, Cantor developed going back as far as 1872. And so we really, in this course, have been working through Cantor's collective papers that spanned 13 years. In our last lesson, I introduced cardinal numbers. This was something that Cantor introduced in 1883. Alongside their arithmetic properties, so we mentioned that we have sort of a less than notion, less than or equal to notion for cardinal numbers. Cantor went further, putting arithmetic on cardinal numbers. So how does one add cardinal numbers and ordinal numbers, which we have not discussed? And in 1892, Cantor proves the theorem, which we will prove on Monday. And this is what is known today as Cantor's theorem. Our book incorrectly gives a weaker statement that is a corollary of the actual theorem of Cantor. What Cantor proved was that if A is any set, then A is not equinumerous to the power set of A. And in addition, this paper gave a new proof that the real numbers are uncountable. So keep in mind that Cantor had already proven that the real numbers are uncountable in 1874, 18 years prior. But his new proof is much simpler, and today we call it Cantor's diagonalization argument, which we will do immediately after proving Cantor's theorem on Monday. Now, Cantor's theorem is profound in the following way. As a consequence of this theorem, we get that there are infinitely many different cardinal numbers, because we get that the natural numbers are not equinumerous to the power set of the natural numbers. But then the power set of the natural numbers is not equinumerous to the power set of the power set of the natural numbers. And we can just continue in this manner ad infinitum and consequently get that there are infinitely many different types of cardinalities for a given set. And this shocked the mathematical community that had already been shocked by the fact that the natural numbers are not in one-to-one correspondence with the real numbers. And Cantor received a lot of abuse from the mathematics community for his results, because they went in the face of intuition, the same intuition that mathematicians have relied on for their arguments. As a demonstration, prominent mathematicians, Leopold Kronecker, Henry Poincaré, throughout Cantor's lifetime, repeatedly attacked Cantor publicly, going as far as calling him a scientific charlatan, renegade, corrupter of youth. These attacks and more led to Cantor suffering from severe depression from 1884 onwards. In 1884, Cantor wrote, "I don't know when I shall return to the continuation of my scientific work. At the moment I can do absolutely nothing with it, and limit myself to the most necessary duty of my lectures. How much happier I would be to be scientifically active, if only I had the necessary mental freshness." And I think we all can agree, mathematics is not something that can be easily done when we are not in the right mental space. And this was something that Cantor struggled with throughout his life, constantly facing attacks from the mathematics community, and his closest ally, Dedekind, Richard Dedekind, who also had worked on the notions of set theory on his own, was not publishing in this realm. And as we will see next week, Dedekind did prove some results that Cantor had as conjectures, but from fear of how the mathematics community will perceive him, did not publish or even tell his colleagues that he had proven conjectures of Cantor. And so Cantor, for the most part, was alone in his endeavor of formalizing the properties of set theory, a work that, as we saw, he continued for the better part of 20 years. Fast forwarding to 1904, at the International Congress of Mathematicians, Julius Koenig publicly humiliated Cantor by claiming that his upcoming work demonstrated that all that Cantor had done in terms of infinite sets was completely wrong. But he did not show his argument when he made this public lecture criticizing Cantor. But when his paper did come out, it was found to be wrong by Zermelo. And you may recognize the name, as Zermelo is one of the founders for the axiomatic system upon which mathematics today is based. And Zermelo demonstrated that Koenig's proof that claimed that Cantor's work was wrong was also wrong, and therefore validating Cantor's argument. And while Zermelo did find the error in Koenig's proof, the damage was done. Cantor had been publicly humiliated in front of the International Congress of Mathematicians. He took this very personally, naturally so. His fight with mental illness worsened with each year, resulting in him being institutionalized for years on end. In 1911, his professorship was terminated, forcing him to retire with no income, resulting in his last years to be lived in poverty, as well as in and out of sanitariums, where he died in 1918. And so this is the tragic life of Cantor. As we have gone through our course, we have seen various results that he published, and we are going to see even more in the coming week. But these were results that were not accepted by the mathematics community of the late 1800s. His work would not be universally accepted until the early 1900s with the work of Frege, Russell, Zermelo, Frankel, amongst others. But by then it was too late. Cantor did not really see the impact that he had had on the mathematics community. As 1915 neared, mathematicians tried to organize a conference on behalf of Cantor and his achievements so that he could see the impact that he had had in the community, but that event was ultimately cancelled due to World War I. And so the main takeaway is to always be mindful that as you go through your mathematical careers, behind all these results that we're doing, there are people behind them. And I'll close my coverage of the history with Paul Cohen's 1963 work, which showed that the continuum hypothesis cannot be proven or disproven in the Zermelo-Frankel axioms for set theory. And so this is what is known as an undecidable result, which comes from Gödel's incompleteness theorems, which assert that there are statements out there, continuum hypothesis being one of them, that we will just never be able to prove or disprove with our axiomatic system. And so with that, let us return to proving statements and start 8.2 formally. The first result that we are going to prove from section 8.2 is the following. Suppose A and B are countable sets. Then the Cartesian product of A with B is countable, and so is the union of A with B. How are we going to prove this? Well, we are going to rely on theorem 815 and theorem 525, which gives us ingredients for proving that a set is countable. Because 815 tells us a set is countable if and only if there is a function f from A to the positive integers that is 1 to 1. So let's see how we're going to use this. So if we do this, let's do our scratch work. So A and B, countable, is equivalent by theorem 815 to the existence of two functions f and g such that f is a function going from A to the positive integers and g is a function from B to the positive integers. And so these are 1 to 1 functions. Okay, so with that in mind, what we want to show is that there is some function h and g. Actually, we already used g, so let's use L, such that h is a function going from the Cartesian product of A with B to the positive integers, and L is a function going from A union B to the positive integers, and these two functions are also 1 to 1. And if we prove this, then we are done, because now then the theorem 815 implies that then A union B and the Cartesian product of A with B are countable. So this is what we want to prove. We want to find a 1 to 1 function. So how do we do this? Well, here's a way. Well, our assumptions give us already functions going from A to the positive integers and B going to the positive integers. And these are 1 to 1 functions. So what if we did the following? What if we define a function? Let's go ahead and call this h. And we're going to go from the Cartesian product of A with B over to a Cartesian product of the positive integers with itself. And this function will be defined h of a comma b, and the way that the function is defined is that we're going to take the input a, since we know that we have the function f going from a to the positive integers, we're going to send a to f of a. So now that's going to be some positive integer. And similarly, we're going to take b to g of b, since we have that b is a function going from b to the positive integers. So then the claim is that h is 1 to 1. And that's going to come from the fact that f and g are both 1 to 1, and I'll prove that in the formal proof. So if we assume for now that we do have this 1 to 1 function going from the Cartesian product of A with B to the Cartesian product of the positive integers with themselves, then we use the following fact. So we know that the Cartesian product of the positive integers with itself is denumerable. So we know that this here is equinumerous to the positive integers. But then that is giving us the existence of another function. Let's go ahead and call this function u. And this function goes from the positive integers, Cartesian product with itself, to the positive integers, with u a bijection. But then, if we take the composition of h with u, so in other words, we are now looking at u composed h, that's a function from the Cartesian product of A with B. So we take first h, And so we get to the positive integers Cartesian product themselves, and then we apply u, which sends us to the positive integers. So the composition is a function going to the positive integers, and this is going to be 1 to 1 by theorem 5 to 5. Because if we prove that h is 1 to 1, the fact that then this function u is bijective allows us to conclude by 5 to 5 that since both h and u are 1 to 1, so is their composition. But now theorem 815 comes to the rescue, because if we have a 1 to 1 function to the positive integers, our set is countable. And so that's how the proof is going to go. And a similar argument can be shown in the case of A union B. So I'm going to skip the scratch work for A union B, move towards a rigorous proof of 1, and then we will rigorously prove 2 via the same method. So here's the start of the formal proof. So I've gone ahead and wrote down what we had in the scratch work. So we're supposing that A and B are countable sets. Theorem 815 tells us of the existence of one-to-one functions f and g going from A to the positive integers and b to the positive integers. Next, we're going to define a new function h going from the Cartesian product of A with b to the Cartesian product of the positive integers with themselves. And that function is defined as h of a comma b goes to f of a comma g of b. Now we want to claim that h is 1 to 1. So let's go ahead and show this. So to prove that something is 1 to 1, we want to take another ordered pair, let's say c comma d, and suppose that h of a comma b is equal to h of c comma d. So to this end, suppose that h of a comma b is equal to h of c comma d. Then we have, by definition of h, that f of a comma g of b is equal to f of c comma g of d, which is equivalent to f of a equals f of c and g of b equals g of d. And now we use the fact that f and g are 1 to 1. Since f and g are 1 to 1, we deduce that a is equal to c and b is equal to d, which is equivalent to the ordered pair a comma b being equal to the ordered pair c comma d. Thus, h is 1 to 1, and that establishes the claim. Now we use the fact that the positive integer's Cartesian product with itself is denumerable. And as a reminder, we proved that statement following our proof of theorem 815. And so, namely, Cartesian product of the positive integer with itself is countable, but specifically, it's denumerable. And so now, returning here, so we have by corollary, following theorem 815, we have that the Cartesian product of the positive integers of itself is denumerable, so it's equinumerous to the positive integers. Therefore, there is a bijective function u going from the Cartesian product of the positive integers with themselves to the positive integers. in particular, we have the decomposition of u with h. So u composed h is 1-to-1 by theorem 5-to-5. And so here we're using the fact that because u is a bijection, it is 1-to-1, and we've already proven that h is a 1-to-1 function. So now the composition is 1-to-1 by 5-to-5. And so now we use theorem 815 to conclude what we want to prove. So we conclude by theorem 815 that the Cartesian product of A with B is countable. And we are done with this with 1. So now let's extend this idea to part 2. So as before, we have A and B, countable sets. So we have theorem 815, we have the existence of 1-to-1 functions, and now we want to define our new function. So next, let H go from the union of A with B, and here's where we're going to take a slight detour. In the previous proof, we did Cartesian product of the positive integers with themselves, since we had the Cartesian product of A with B as our domain. But now, when defining H, we need to be careful, because it's a union of A with B, and A and B may not be disjoint. So we need to take special care for elements in the intersection of A and B. And so what we are going to do is define a function not going to the positive integers, but rather to the integers. And the way we're going to define this function is in the following way, where we're going to take h of x. And so now we note we have two functions, f and g. And what we are going to do is send x to f of x if x is an a. And we're going to send x to now the negative of g of x. But if we were to simply say if x is in b, this is wrong. Because an input that lies in the intersection of a and b, if it were non-empty, would now have two different outputs. And so we can't just say that we're sending x to negative g of x if x is in b, but rather we want to take the set difference. And so now we're going to go ahead and write here if x is in b minus a. And so that guarantees that x is now going to be in b, but not in a, which will make h a function, since now every input will have exactly one output. So that's our function h. We claim that h is 1-to-1. And the proof of this is going to be similar to the argument that I just gave for part 1. So I leave this to you for you as an exercise. So prove this. And I recommend pausing the video, proving that h is 1-to-1 for practice. But now if we have that h is 1-to-1, now we do the same trick we did earlier. In the previous proof, we constructed we used the fact that the positive integers, Cartesian product itself, was equinumerous to the positive integers to define, by definition, a function u, or I should say to find a bijective function u between those two sets. Well, here our outputs are the integers, and we know that the integers are countable, namely the numerable, so there's a bijective function to the positive integers. And so here we continue. So since the positive integers is equinumerous to the integers, there is a bijective function u going from the integers to the positive integers. Consequently, by theorem 525, we have that the composition of u with h is 1 to 1. But now this is a function going from a union b to the positive integers. And now we use theorem 815 to conclude the proof. So by theorem 815, we conclude that A union B is countable. And that does it for theorem 821. So we are done. The next result we're going to prove is theorem 822. And this is the motivation for Hilbert's thought experiment on Hilbert's hotel. And so this is Hilbert's hotel in a mathematical form. So what does this theorem state? And how is it connected to the thought experiment? So the theorem tells us that the union of countably many sets is countable. In other words, if F is a family of sets, F is countable, and also every element of F is countable, then the union of F is countable. So what does this mean in the context of Hilbert's hotel in its most general form? So recall that with the more general form of Hilbert's hotel, we have the innumerably many buses, which we label with regard to the natural numbers. And so we have bus 1, and there's infinitely many people in this bus. And so let's go ahead and say that we have like the person in seat 1, then the person in seat 2, seat 3. But there's infinitely many people here. But then we have another bus, also has infinitely many people, labeled appropriately with the positive integers. And then we have the third bus, but then we have infinitely many buses, but infinitely many in the context of the positive integers. We have 1, 2, 3, 4, 5, so on and so forth buses. But we also have the people that were originally in the hotel. So people originally in the hotel. And then the question is, can we accommodate everyone in this hotel, given that it is already full to begin with? And so what we really are doing is taking the union of all the people in the hotel, and then correspondingly with everyone in the infinitely many buses, but the innumerably many buses, and taking the union of all of those. And so we have, if we label this, the people inside the hotel to be in the set A sub 0, the people in the first bus to be in A sub 1, the people in the second bus to be in A sub 2, A sub 3, so on and so forth, the nth bus will be A sub n, then we're looking at the union of the A sub n's, but now we're taking this over all the natural numbers n, since we're starting at 0 for the people originally in the hotel. And what theorem 822 tells us is that because each of these sets A sub n is countable, and yes, we have a total of countably many sets in our set of sets, F. So in this example, F is just A sub n, and in the naturals. Each A sub n is countable. So the theorem tells us that the union of the family of sets, which is equal to the union of the A sub n's, that this is countable. And consequently, since in this example everything is infinite, we end up getting that the union of the A sub n's and in the naturals is equinumerous to the positive integers. And now this bijection here is the one that allows us to give every person a unique room in Hilbert's hotel. And so that's how theorem 822 leads to Hilbert's famous dot experiment. But how do we prove this? And so that's the next step, proving this result rigorously. So let's get started with the proof of theorem 822. So we're supposing that F is a family of countably many sets, each set in the family being countable. If we break this down via the definition of what it means to be a family of sets, we end up getting that F is equal to the set of A sub j's such that j is an I, where now I is a countable indexing set, and each A sub j is countable. But now, since I is countable, we have two possibilities. We have that I is equinumerous to I sub n, and so just notice bad notation here, but again, this I sub n has nothing to do with I, but this is just those i's in the positive integers such that I is less than or equal to n. Or I is equinumerous to the positive integers. So in particular, F is equal to the set of A sub j's, where now j is in j, where j is equal to I sub n for some natural number n, or j is equal to the positive integers. So now this has the following benefit. This allows us to talk about the sets in the family of sets as being A sub 1, A sub 2, A sub 3, so on and so forth. And so let's use that to our advantage. But we first have to eliminate the possibility when j is equal to I sub 0. So suppose that j is equal to I sub 0, so in other words, the empty set. Then what happens? Well, if that's the case, F is just the empty set. The family of sets is just the empty set. And the union of the family of sets, in this case, is just going to be empty. And thus, this is finite, so it's countable. So that takes care of the case when j is equal to the empty set. So we may assume that j is not empty. So we may assume that j is not equal to the empty set. So while we are on the case of the empty set, let us consider what happens when one of these A sub j's is equal to the empty set. So next, suppose that A sub j is equal to the empty set for some j. Then, if we take the family of sets, the union of the family of sets, this is going to be equal to the union of the family of sets if we remove that A sub j, or in other words, just removing the empty set, the set containing the empty set, from F. And so, it suffices to show that union F is countable where each A sub j is non-empty. And so that's what we are going to do now. So now we can assume that every single A sub j in the family of sets is non-empty, which in turn allows us to choose elements in those sets. Now, let us continue. We know that every A sub j is countable, and so since each A sub j is countable, we have that a sub j is equinumerous to k sub j, where k sub j is equal to I sub n sub j, or k sub j is equal to the positive integers. And so here, n sub j is a positive integer. And so let me just go ahead and write this way. So n sub j with n sub j being a positive integer, or k sub j being equal to the positive integers. Now, what is going on here? Because there's a lot of notation. So all that we're saying is that since a sub j is countable, it's denumerable or finite. But the thing is, we're working with countably many j's. And so I am being careful by writing k sub j to say that a specific a sub j has a corresponding set k sub j of the form I sub n sub j with n sub j positive integer. Keep in mind that we've already taken care of the situation where a sub j is empty, so we know that every single a sub j going forward is non-empty. So that's where the positive integer is coming from. And then in the case that it is denumerable, then k sub j is equal to the positive integers. So now, this gives us a bijection. So hence, for each j, there is a bijective function let's go ahead and call this function f sub j, going from k sub j to a sub j. And so now this function is bijective. And now what we are going to do is label all the elements in a sub j in a way that we are indexing over the positive integers. So next, we're going to let f sub j of m, so the inputs of f sub j are in k sub j, where again, either it's the positive integers or a subset of the positive integers. And so we have a sub j of m, and we're going to be sending this to an element. This is of course going to be an element in a sub j, but now we're going to do the following label. We're going to write a sub m comma j. Actually, just to keep in line with the book's notation, okay, this is good. M sub j. If you keep in mind in the book uses the notation a sub m, and then it uses a superscript. And so I'm just going to use the comma. And so that's the only difference between my notation and the text. And so we have a sub m comma j. So note that a is then equal to a sub j is equal to a sub 1 comma j, a sub 2 comma j, a sub 3 comma j, so on and so forth, or in a more succinct manner, this is the set of elements of the form am comma j, where now m is in k sub j. And so now we have that for every a sub j, we can list the elements in order of the positive integer. So we have a first element, second element, third element, because of this bijection. And now we are almost done. So let's go ahead and now get to the final step of the proof. So I need a bit more space. So consequently, the union of f, which is the union of the a sub j's for now j in our indexing set, which we called capital J, is the same as when we take the union, we're taking the union of all the sets that have this form. And so we're going to have elements of the form am, comma j, where m is a positive integer and j is a positive integer. So in other words, we have an ordered pair. In the Cartesian product of the integers with themselves. So lastly, let G from the Cartesian product of the integers with itself to the union of f be defined by G of m comma j is equal to a sub m comma j. By construction, this is an onto function. G is onto because every element in the union of the family can be written as a sub m comma j for some m comma j in the Cartesian product of the positive integers of themselves. So if we took some random element in here, it has this form, and now we have G of m comma j maps to it. So that's what I mean by construction. G is onto. But why is this good? Well, let's take a step back and recall theorem 815. In the proof of theorem 821, we use that if we have a one-to-one function from a to the positive integers, then a is countable. But theorem 815 also has another equivalent notion, namely that if we have a function from the positive integers onto a, then the set is countable. But what we have now is a function that is onto from the Cartesian product of the integers with themselves to the union of f. And so, since the Cartesian product of the Cartesian product of the integers themselves is equinumerous to the positive integers, there is a bijective function h going from the positive integers to the Cartesian product of the positive integers themselves, and thus the composition, where now we take G compose H, and this will go from the positive integers to the union of f, is onto. And now we use the theorem 525, which tells us that if we have the composition of two functions that are onto, then so is the composition. So we have theorem 525, and thus the union of f is countable by theorem 815, since now we have the existence of a function that is onto. And that concludes it for today's lesson. So we have proven the theorem and consequently the reason for why Hilbert's thought experiment is true. And it's just theorem 8.22 done in a concrete setting with a hotel and guests and the hotel's full. But even if we have innumerably many buses, we can still accommodate everyone in Hilbert's hotel. And now the question remains, what happens when the sets are denumerable? And that's what we are going to investigate with our next lesson.